Hello everyone and welcome to the tTmu seminar on temperature, time and chemical potential dependence in quantum field theories. Today we have the pleasure to welcome Raju Venugopalan from Brookhaven, who will talk about the word-line formalism in quantum field theory and its applications. So please, Raju, take it away.
Thank you very much for this invitation. What I'm going to talk about is some work that I've been doing on world lines in the high energy, with the high energy limit of QCD in mind, and this kind of led me sort of to quantum computing, not the other way around. So I'm really a novice in the field of quantum computing, but fortunately I have some really extremely bright young people I'm working with. João Barata, Nicholas Mueller, and Andre Tarasso, who have sort of taught me everything I know, the limited amount I know about this field. So my interest in world lines was really motivated by thinking about the anomalies in the high energy limit of QCD. And I will actually be reporting on some work on that next week, some exciting work with Andre Tarasov in the context of uncovering some of dynamical features that in deep elastic scattering. So without further ado, so as I was saying, so I'm going to give you kind of an overview of the problems that we want to address, where quantum computing in some fashion may help us make progress. But this is very much sort of a, small steps for small feet kind of approach to things, which hopefully will lead somewhere. So if I go to my next slide, let's see, how do I change? Oh, okay. So anyway, so this is the outline of my talk. I'm going to talk a little bit about deep elastic scattering, why is of interest, what is the QCD landscape of problems that we want to address, in particular the Regge-Limit QCD. And then I will talk about the borderline formulation of QCD very briefly, and how it can be used to formulate the problem of computing structure functions. And then I will use that to motivate a hybrid quantum classical approach, which may already be may be implemented in some simple fashion in terms of very simple toy models and their extensions in the noisy intermediate computing era, intermediate scale quantum computing era. And then I will talk about how this very simple example that I've given can be expanded both in scope and complexity, which, if achieved, would be extremely exciting. So that's a motivation for pursuing these problems. So I should give you a little preliminary on deep elastic scattering. I know that many of you are not working on this field, and for those who are, I apologize for the very simple introduction. So what is deep elastic scattering? It's the process whereby you have a very high energy electron scatter a high energy proton or nucleus, some hadron, and it scatters off at some angle with some change in energy, emitting a virtual photon, very energetic virtual photon with some forward momentum q mu that probes deep inside the structure of the hadron. So the simplest inclusive measurement, where you only measure the outgoing electron, you can write that in terms of invariance, which are the resolution power. So that's q squared. It's the forward momentum squared. It's a Lorentz invariant. And then in terms of the energies and angles, can be written in this form here. There's the inelasticity of the process, which is the energy of the virtual photon divided by that of the electron. So that's sort of the QED part of the process. And then there's novel thing that was discovered 50 years ago, which is the Bjorken X variable, which is the other Lorentz invariant, which can be written as q squared divided by the central mass energy squared, that's this S here, times this inelasticity. So going to very high energies in QCD is like going to small values as the Bjorken X variable. which has the interpretation in Feynman's parton model as being the fraction of the longitudinal momentum of the proton that's been carried by a parton, a quark or a gluon. Now, in addition to this inclusive process with polarized protons or nuclei, where you only measure the electron, you can measure a lot of different things. So these inclusive measurements give you your structure functions, the parton distribution functions. For unpolarized protons, there are the F2 and longitudinal structure function. For polarized protons, you have a slew of them, G1 to G5. But that's not all. So you can do, semi-inclusive measurements where you measure electron coincidence with some kind of hadron or jet. You can do exclusive measurements where you measure electron, photon, or hadron, and the proton or nucleus remains intact. And you can finally do diffractive measurements as well, where you can have electron, hadrons plus jet plus some kind of rapidity gap, but there's no color, and possibly even have an intact proton or a nucleus. And these can be expressed in terms of so-called diffractive structure functions. So there's really a range of ways to poke and prod inside the hadron and nucleus, polarized or not, to really uncover the dynamics of confined partons inside hadrons and nuclei. Now, one can also do things like measure nuclear fragments, multi-particle correlations. So this is really a very rich set of things one can do. So why am I talking about this? It's because there's been tremendous excitement recently because the United States has finally decided to build a collider. And that's a new collider, and that's the Electron Ion Collider, which will be built at my laboratory, Brookhaven National Lab. And it will be operational in about 10 years at a cost of around $2 billion. And that will smash very high energy electrons up to 18 GeV into protons, which are polarized, up to 275 GeV, or atomic nuclei at 100 GeV per nucleon. And that will really, really explore many of these final states that I was talking about. Now, there was a previous such collider in Germany, not too far from you in Hamburg, at DAISY, called Hera. It's a lower energy machine than Hera was, but it will have about 1,000 times the luminosity of Hera. So it's somewhat lower energy. It's about a factor 2 or so, 2.5 lower center of mass, but the luminosities are huge, and you can look at polarized protons and nuclei. So one can really, it's really a QCD machine to really understand QCD in great depth and detail. And so that's kind of the motivation for why one's interested in deep elastic scattering again. From the physics point of view, what are we trying to learn? It's the realization that even though we've learned a lot about QCD, there's really a tremendous amount that remains unknown. And being the paradigmatic quantum field theory, that's a value for all of theoretical science, because embedded in QCD are many of the highly non-trivial features of quantum field theories. And so that's just to give a sense of what we know and what we don't know. Here's a cartoon of the landscape of strong interaction, where one goes up in resolution with increasing q squared. So that's the full momentum squared I introduced. And one can go high up in parton density or by going to smaller x or higher energies. So much of what we know about the strong interactions are really in the upper left corner and lower left corner of these plots, where in the upper left corner we have perturbative QCD, which works beautifully, especially now at the LHC. It's truly showing its power. And so we know that this is, correct theory for sure. And likewise, the lattice has really taught us quite a bit about static properties of the theory. So we say our claim to QCD being a robust quantum field theory is really based on its non-perturbative realization of the lattice, which has been used with great power and efficiency recently. So to let us believe that this is truly the correct theory of the strong interactions. However, when we go along these landscapes as formulated in terms of these q squared and energy or parton density, there's really much that we don't know. And I want to point out that that's really the bulk of high energy cross sections. This is outside these two anchors on the left of the plot. In particular, if you start at very high q squared and you start going to high energies, then you start really probing sort of so-called higher twist correlations, which are really, in the language of condensed matter physics, these are multi-body, multi-parton correlations. And it gets harder and harder in the language of perturbative QCD, and we don't really have a very systematic way to go very far without getting into trouble. Likewise, a lot of soft physics, what is called soft physics, which we use to understand backgrounds of the LHC, has long been known to be expressed in terms of effective degrees of freedom, like Pomerans, Regions, all-arounds, and so on, really coming from S matrix theory. But we don't really have a deep understanding in the underlying theory of how these structures emerge, or if they are generally meaningful or just some parameterizations of data. Now, an interesting possibility that was realized was that if you are in this right side of this plot and you go up in resolution at very high energies of small x, then matter, the partonic matter becomes highly dense, becomes really high occupancy matter. And when it's a very high occupancy, there's an emergent scale in that regime. And I'll talk about that in a second. But because of that, in principle, one can use weak coupling techniques to understand very strong field physics in QCD. And that may give us a way, just like in condensed matter physics, when you write down the right effective theory in the vicinity of the critical point, then that effective theory can sort of give you a better description of phenomena around there and maybe allow you to go a little further in these directions as well. So there are many open questions in deep elastic scattering, but that's driven by the fact that the theory gets very hard when you go outside these two corners that one has, and one is forced to resort to various effective descriptions to understand the dynamics. Now, in the Regge-Limit, I just wanted to mention, because I'm going to be talking about that later on quite a bit, or at least it's going to be implicit in what I'm going to be saying. So in QCD and in gauge theories, that corresponds to the limit of very high energies, fixed momentum transfer, which is typically small. But in DIS, one of the nice things is that this momentum transfer, which is given by q squared, can be quite large too. So you can also have a scale which is much larger than lambda QCD, even when you go to this x going to zero limit of the theory. So as I said, there's novel dynamics that comes in QCD in that regime, where the density of partons become very large and they start to close pack, as shown in this transfer section of the hadron. And QCD, we believe that these would have a maximal phase space occupancy. Gluons carry color charge and they resist close packing. And there are many body correlations that really that turn on. These are so-called higher twist effects as shown here. So if you have Bremsstrolling and more gluons as you go from low energies to high energies, at sufficiently high energies, there are recombination and screening effects, which are all twists. So in the language of the operator part expansion. And there's an effective description that emerges in terms of classical fields, which have an emergent scale, which is given by this saturation scale here, the close packing scale of gluons in the hadron. So this is kind of one effective description of the Regge-Limit, and this is something that I will return to later on in my talk. So returning to the problem, of the general problem of computing deep elastic structure functions, what really is the problem in computing these? Why can't we actually do this from first principles? After all, one could say that, well, when you compute, say, the hadron tensor in deep elastic scattering, which is proportional to these structure functions, What you're doing is you're introducing two electromagnetic currents in the amplitude and the complex conjugate amplitude, as shown here, for this plot, and that corresponds to the time-ordered product of these two electromagnetic currents at different space-time locations, which are inserted into this hadron state here, given by P and S. And then it's just taking the imaginary part of this. Now, this, of course, can be very complicated because there are many different configurations for this virtual photons to interact with. So at high X or low energies, you would scatter off the valence partons inside the hadron. And at high energies, you could scatter off these C quarks, which are produced by proliferating gluons as you go to higher and higher energies. So it may be difficult, but then you can say, well, why can't we do these computations? So as you go to higher X, the problem becomes especially hard because it's very dynamical. So these kinds of configurations are very short-lived. They have very large invariant masses. And Monte-Carlo lattice computations, which would be the way in lattice gauge theory to compute objects, correlation functions, are performed in Euclidean spacetime or imaginary spacetime. So this is extremely difficult to do, and we don't really know how to do this in a very efficient way. The operator product expansion, for example, offers one path, really breaks down at small x, because as I mentioned, you get all twist contributions becoming equally important. So especially in a regime of high energies, this problem seems virtually impossible. So it's really an outstanding problem in theoretical physics to start from first principles in QCD and compute things in this high energy regime.
So Raju, can I have a question?
Sure.
So were there any lattice attempts whatsoever, or is like completely beyond reach to the extent that nobody really attempted?
So you mean so at large X, of course, there's been a whole subculture or subset of people actually trying to compute moments of structure functions and so on in the lattice. So that's a very highly developed but very difficult enterprise. I mean, and in practice, one sees how difficult it is to actually do it. At small x, it's really very, very few attempts. There was some attempt by Nachman and collaborators in some approximate kind of framework, and so there's really been so there've been attempts on the lattice to compute autocorrelation functions directly, but again, their focus really has been kind of in this large X region. So I think the small X problem is really terra incognita from that perspective.
Okay, thanks.
So so the question is there an alternate way to make progress in this apparently insuperable problem from first principles? And one can ask, is quantum computing a possibility? After all, one of the fathers of deep elastic scattering, the parton model, Feynman, was also the father of quantum computing. So you think, well, maybe he was thinking about these kinds of problems when he was formulating this. So can one, start from the quantum field theory, which is formulated in this infinite dimensional Hilbert space, and formulate problems on a quantum computer where you have some finite dimensional Hilbert space with qubits and unitary gates. So it's sort of a quantum mechanical representation of this quantum field theory framework. Now, this is a Hamiltonian approach. Firstly, because one wants to understand real-time problems, you want to understand the usual evolution of a Hamiltonian operator, which is sandwiched, between these proton states. So the one approach we know in QCD is the Kogut-Susskind Hamiltonian for lattice gauge theory, there's some discussion in the literature, and I'll come to that in the very end, is how to try and realize this in a sort of discretized form, which is applicable to such real-time problems. Again, this is a very difficult problem, and the focus has been on smaller systems and lower dimensions, at least in this present era. And there's really serious complexity due to gauge invariance and implementing Gauss's law and so on. Also, in thinking about this problem, it may be useful to think about, say, different approaches for different kinematic regimes as an outset, because as I said, at large X, the physics is less dynamical, so to speak. One is probing fewer degrees of freedom, perhaps, it might be sort of there may be a certain approach that may be more effective approach that may be more valid at larger X than at smaller X. So this is one of the questions that one can think about in trying to use quantum computers to make progress. So so what I'm going to be talking about is a Wehrlein formalism of gauge theories. And one can ask, how does one formulate structure functions in this approach? So this is this Wehrlein formalism can be formulated in Schwinger-Keldysh contour, which is the appropriate one for computing real-time correlation functions. And generically, one can sort of break up this problem into two parts, where the QCD path integral in this kind of Schwinger-Keldysh framework can be expressed in terms of sort of initial conditions at minus infinity for Yang-Mills fields, and for fermionic fields. So these are what I call valence degrees of freedom, which are in this Z sub f, which is the Dirac part of the QCD action, right? So these are the fermionic fields, and this SCQ is the Dirac action. And then, of course, you have the path integral over the Yang-Mills action. Now, what the Wehrlein approach here is to actually compute the Z sub f explicitly in some systematic way. That is going to be kind of the essence of the strategy here, whereby one could think about computing the Z sub f in a quantum computer in terms of a unitary evolution of what I will discuss are these quantum mechanical Wehrleins, where the internal symmetries can be described in terms of spinning and colored Grassmann variables of point objects, which will be these internal symmetries can be represented qubits, these point-like objects in processing in these background fields, right? So these gauge fields here. So one can kind of try and break up this problem in terms of computing this part in some background field using a Wehrlein framework, and then finding a way to compute the whole thing in terms of forming this path integral over the gauge fields. So this is sort of the essence of this Wehrlein approach.
So
yeah.
Another question. So what would help you in evaluating the second path integral?
Sorry?
You're trying to imply that the first path integral over the fermions is kind of hard to compute, and the second one is going to be easier?
No, it's the other way around.
Oh, is the other way around?
It's definitely the other way around. So I mean, fermions are kind of natural qubits, while the big problem in quantum computing has to do with bosonic degrees of freedom, as I'll discuss.
So you want to employ quantum computing for both? That's your idea.
Well, that's so the ultimate idea, the ultimate goal, of course, if you want to really solve the full problem, is you want to put the whole thing on a quantum computer, right? But I think what I'm going to, I think at least in the near future, that is highly unrealistic, because just the cost of implementing the gauge action on a quantum computer is enormous. You need millions of qubits. This is a kind of what I'm going to talk about is a kind of hybrid approach where you try to describe some degrees of freedom on a quantum computer, and others you use just classical computing to compute that, and you combine the two in some systematic way. So that's the goal, at least.
Go ahead, thanks.
Should I go on?
Yeah, sure. Yeah,
okay.
Unless there are other questions, of course.
So this is probably a good point to ask a question, because I'm now going to talk about this part here in terms of the word line formalism. So what's a word line formalism? So just so there's some nice reviews here if you want to take a look. In particular, in sort of the modern language, there's a very nice paper by Strassler, which is almost 30 years old now. What Strassler showed was that, and I'll come back to this later, was that there's sort of a really concrete relation between this Wehrlein approach and the string amplitude formalism for computing, n particle, tree level and one loop Feynman diagrams, which was pioneered by Bern and Kossover. So this is really a one-to-one between these two languages. So that's kind of prompted a lot of interest in the sort of field theory community in terms of sort of understanding this formalism. And there's a nice review by Cardini and Schubert. So the basic idea goes back to Schwinger, like a lot of things, and it's basically this simple observation that you have some log of some object. You can write it in this form here, where this, in a kind of heat kernel kind of form, where this sigma can be written as some proper time kind of integral over some e to the minus sigma t. Okay. And so what this means is that in the concrete example here, so if you consider, for example, one loop effective action of a massless scalar field coupled to an abelian background field here, then you can write the effective action in terms of some log determinant of this d squared operator here. Okay. And so this is the same thing as trace log, right? And then this log can be, using the Schwinger trick, can be written as traces exponential minus t times d squared, which is sigma here. And then what you can do is you can sandwich this object between quantum mechanical coherent states and write the result in this form here, where now this is a path integral in configuration space of a path ordered exponential of this point particle, which is represented by this term, and it's coupling to the background gauge field here. And epsilon is the Einbein, which is familiar to people who deal with general relativity. It's the square root of the one-dimensional metric. Now, this formalism has, of course, been applied to spinors in vector, axial vector, and all kinds of complicated backgrounds. And in particular, for our case, we think of this kind of spinor action where A is a vector gauge field, B is an auxiliary axial vector gauge field. Now, if you have such an auxiliary axial vector gauge field, then the fermion effective action, after integrating out these fermion fields psi r, can be written in terms of a log determinant, like previously, where chi is now this Dirac operator. Again, now with this term gamma 5 times b. Now, because you have this additional term, the effective action also has an imaginary part. And this is really an elegant way to represent the chiral anomaly. So what you can do is you can introduce this auxiliary axial vector field, and then this really contains all the information from the measure that you've integrated out. And then if you if you take functional derivatives with respect to b and put b equal to 0, that's what gives you the anomaly. So this one can show this explicitly in a very nice way. Oops. Okay. So, that said, again, following this word line approach, you have this kernel, this log determinant, which then you can write now this log determinant again in terms of trace log, and then do the same thing as previously. But now, because you have spinors, you not only have boson coherent states, quantum mechanical coherent states, but you also have fermionic coherent states, which are these grass mounts that you're sandwiching this trace log of this chi in between. And so this was in particular is a very nice paper by Hoker and Gagne, this is discussed from about 15 years ago. But there's a lot of work in sort of old-fashioned string theory, which actually predates this. And the basic idea then is you have this kind of Wigner-Weil formalism where you can write down your Clifford algebra in terms of these creation relation operators, construct fermionic coherent states, which are Grassmannians, which are these thetas are complex Grassmannian eigenstates. But you can construct you can also work with their corresponding Majorana fermions. It's this real representation of these little psi i's. Okay, so these are Grassmannian objects. So what you've done is you've started from the determinant, right? You've log determinant, the effective action, and then you have this heat kernel representation using trace log of chi, and then that you sandwich between bosonic and fermionic coherent states, okay, and that's the approach. This W of I will sort of ignore because I'm not going to be talking about the anomaly in the rest of this talk. So then following this procedure, one can compute the one loop effective action. So again, you have this dt over t that you had. This is sort of Schwinger's trick, and then you have this dx dp. This is this path integral in configuration space of point particles. But now you have this deep psi. These are these Majorana fermions of your action, which is now the word line action here. So you can write it in this form here in terms of this word line action. So essentially, when you insert these fermionic coherent states in the trace log, you can sort of do the usual sort of quantum mechanical thing of introducing lots of intermediate states, and then you can rewrite this in terms of an action. And the action is very nice. It really looks like a nice point particle action, which is p mu x dot mu. And similarly, you have one for the fermion, so this psi dot term, which is very important. And you have this H Werlein Hamiltonian. So if you have a QCD plus QED Hamiltonian, you can write it in this form, which is p squared, where p is p mu times g mu for the QCD and QED fields. And then you have this psi mu f mu nu psi nu term. That you have also in the Hamiltonian, which contains all this spin dynamics. So you've somehow separated out the bosonic and fermionic dynamics sort of explicitly in this framework. And in QED, actually, there's a supersymmetry between these fermionic and bosonic variables that's explicit. It corresponds to a Q equal to 1 supersymmetry. For n equal to 1 supersymmetry. And so what we have done in this process is a kind of requantization of second quantized fields. So we've gone from kind of QFT framework that we started with to something that really looks like quantum mechanics. Now, okay, so why is this nice? Because one thing you realize is that it has sort of a very beautiful semi-classical approximation. So if you take the saddle point of this Werlein Hamiltonian, then it turns out that these have very these are give you sort of well-known semi-classical equations which describe processing spinning particles in background fields. So for example, in QED, that's the Bardman-Michel-Selegdi equation. So that tells you kind of the gyromagnetic moment for a spinning particle in a background field. In QCD, these would be the Wong equations that describe, colored particles processing in gauge field backgrounds. And then there's an analogous one for spinning massive particles in gravity. So these are very useful if one wants to build up some kind of semi-classical intuition in quantum field theory, in terms of things like Wigner functions, in particular for theories with internal symmetries like spin and color. And I have several papers with Nicholas Mueller where we've sort of discussed some of these semi-classical approaches, in particular in applications to constructing chiral kinetic theories for a variety of problems in different contexts. I should mention that there's also a kind of the semi-classical approximation can also be thought of in sort of the Euclidean framework as a kind of Whirlwind instanton, which is the saddle point solution of this with periodic boundary conditions. And that has been used to compute pair production up to 2 loops in QED by Schubert, Dunn, and their collaborators. So now with this preliminaries, let me go to DIS in the Whirlwind formulation. So you can write down now this hadron tensor, which is the product of these currents. In terms of sort of a following expansion now, where recall again, I've expanded out the Whirlwind action. And so when you expand out the Whirlwind action, now the objects are these bosonic and fermionic variables that you saw here. But then now, again, in this Schwinger-Keldysh kind of framework, that involves computing the following density matrix, where you represented the proton now in terms of these configuration space bosonic and fermionic variables and the gauge fields that they live in, right? So this object in the proton can be in the Whirlwind framework can be written in this term form here, where now these U's are these unitary evolution operators that give you the time evolution between x and naught, right? And that Hamiltonian is the usual Yang-Mills Kogut-Susskind Hamiltonian plus sort of a Whirlwind Hamiltonian for quarks, okay? And these currents can also be written, again, in this Whirlwind approach in terms of these bosonic Whirlwind degrees of freedom, which is given by this tMuK for each Whirlwind, and then these fermionic Grassmann variables here. Okay? So now, as I said, this kind of what we're going to do is, so this is kind of writing the full problem in this fashion, the level of this one loop effective action. In terms of Whirlwinds. And then the question is, can we now simplify this problem somehow and try to understand this Whirlwind dynamics on a quantum computer? So here one can sort of visualize this hybrid formalism in the following way. So again, here's my deep elastic scattering process. Now, turns out that the description of the background fields in which these Whirlwinds couple to simplifies enormously in the Regge-Limit. And that's just because of this Lorentz contraction property that one has of gauge fields, is that you can really think of these as kind of shock waves which interact, just like 2 instants of time on this quark loop here, for example. So one can sort of quantum compute this part here in a Whirlwind Hamiltonian, and then the rest is a kind of classical computation that one does in some fashion here. So the hadron tensor that I had there in the previous slide can be rewritten in a form which has sort of a classical part here, where you have large X sources with some distribution here, which source the gauge fields, the background fields, which are these highly Lorentz contracted kind of shockwave fields, which then couple. So since it's DIS, I have the polarization tensor of this given by this quark loop here in the background field, and then where the Whirlwind comes in this is the effective action. So this is kind of the Whirlwind Hamiltonian. Okay, so this problem can further be simplified by taking some classical approximation of this whole saddle point here of gauge fields. So that would be the simplest thing one can do. And as I argued to in the high energy limit, you can replace this by classical fields. Okay, so this is kind of the gluon shockwave approximation that one has. So alternately, one can think of a different kind of background field in terms of, say, a sum over plane waves. Okay, and I remind those who may know this that this actually is what generates this Bernoulli crossover in gluon one-loop amplitudes in the Worldline formalism. So if you were to expand out these gammas and use this kind of plane wave background, you would sort of get all these, n particle one-loop amplitudes, which are efficiently then being computed in terms of this gammas of A's in the Worldline approach. So one can then go and say, okay, let me think of the most trivial problem that one can have, even with these simplifications. And the simplest thing would be to compute these traces, just to get a handle on how one would start even building up thinking about quantum computing. So these objects here, these traces, when one does it in the Worldline, the simplest thing can be written in terms of these Majorana fermion bilinears, psi minus psi plus, and so on. And in this case, since these have a natural kind of coherent state representation in terms of creation relation operators, you can write those in a spin basis in an almost trivial way, as shown here in terms of Pauli matrices. Okay. And these are then sort of natural qubits. So there's a natural qubit representation of this trace here. And one can write down the corresponding trace to just compute this very simple thing. And so this is a quantum circuit where you start with, say, n qubits, which is represented by this identity here, which is given by Pn. It's a maximally mixed state. In our case, we just consider, for this problem here, just 2 qubits. And then you start with a control qubit. You kind of entangle this through a Hadamard gate. And then this is your control for actually measuring this omega that I had here, which was these fermionic Worldlines. Okay? And so then when you do this combined measurement with this quantum circuit, you get some entangled density matrix here, which you can then measure on a Pauli basis to really reconstruct this trace that one had in this previous slide here. So this is kind of like the simplest toy thing one can do. It's a kind of almost trivial kind of representation of the simplest part of this problem. So of course this is not where we want to be. So one can ask about expanding this treatment in scope and complexity. And so the first thing is that, okay, let's just discuss scope. And I just want to remind you again that the logic for this Worldline thing is to compute scattering amplitudes. And these techniques have been employed to compute perturbative amplitudes in a number of contexts. So, for example, soft gluonary summation to high loop order, and so on, as discussed by these guys here. But more generally, that if one can represent these things on a quantum computer, as the Worldline representation suggests, then it tells you that there may be some kind of a point particle or a quantum mechanical representation of the quantum field theory in computing amplitudes, which can replace the factorial growth of complexity of computations as you increase the number of final state particles in the order of perturbative expansion. Now, this is not a new idea. I mean, the paradigmatic framework for that was suggested by Jordan, Lee, and Preskill in this paper, and even maybe before. And here's the abstract of the paper, just to give you a sense, where they really developed a quantum algorithm to compute scattering amplitudes in a massive 5-4 theory in 4 and fewer dimensions. And they argued that the algorithm is polynomial in time, the number of particles, energy, and precision, and therefore offers an exponential speed up over existing quote-unquote classical methods, which have this problem that you have a factorial growth in complexity as you increase the number of particles and the order of the perturbative expansion. So what we are working on is an explicit realization in a single particle digitization strategy to compute to compute scattering amplitudes in this kind of hybrid approach. And so just to return to what I had before, so recall that my Hamiltonian for the whirl lines was, Yang-Mills Hamiltonian for the background fields and the whirl line Hamiltonian, where the basis states of this Hamiltonian are x and theta from the whirl lines and the gauge fields from the Yang-Mills Hamiltonian. Now, what I talked about very briefly in that toy example was just how to treat the internal symmetries. And that's kind of relatively simple, as said, because these are sort of natural qubits and there are not very many of them. The big problem is in the digitization of these bosonic whirl lines. Okay? And so that's kind of the big challenge, and even in this hybrid approach to kind of go beyond the very simplest trivial toy model example. Now, the gauge field problem is as I said, a tremendous problem. If one were to solve that, then one has to solve real-time QCD, so it's really kind of a tremendously difficult problem. So our strategy is at present to treat it classically. However, I should mention that there have been really several interesting digitization approaches which really go back to kind of sort of these rigid rotor representations of the Kogut-Susskind Hamiltonian, back to the work of Horn, Orland, and Rohlik. There was really very beautiful work done by Silas Chandrasekhar and Uwe Wiese and their collaborators, which is continuing. There's also kind of complementary work by Erez Zohar and collaborators, Resnick, Chirac, Cross, Borello, and so on. And there's many different realizations, either in terms of Rishon types fermionic representations of link variables in the Kogut-Susskind Hamiltonian, or sort of the discrete representations of that, I should say, or in terms of, say, so-called Schwinger boson representations, which is another line of attack. Now, but as I said, for the moment, we would treat it classically. I'll come back to this point at the very end. So these single particle digitization strategy means that I want to write down my Hilbert space for these objects as a kind of direct product of single particle Hilbert spaces, where for each particle I have some momentum. I have representing all the different momentum states by a finite number of qubits. And then I have the vacuum, and then so I can either write this in momentum or in a position basis. Now, this approach is distinct from that of Lee Jordan and Preskill, because their construction is in the basis of Heisenberg field operators, phi and pi, as opposed to in terms of the single particle basis, which is motivated by the whirl line approach. So what this digitization approach really corresponds to in practice is kind of a binary qubit representation of the momentum states of each particle. So these can be represented by sort of log of the number of possible momentum states. So that's the number of qubits that one would require to represent each particle. So there's you can represent the absolute momentum by log of these. Then there's a binary representation where you can represent the sign by qubit and the occupancy of the qubit by whether it's occupied or not by one qubit. And this is kind of a construction that we have developed, which actually implements this binary representation of the single particle discrete Hilbert space. Now, so it's only kind of, so if you have, m particles, then it's really roughly m times n Okay, so it's really the resources for this only scale logarithmically with the number of single particle states. So now, of course, once one has constructed such a basis, then you want to build the m-particle Hilbert space, for Bose or Fermi symmetrization. And so here, for example, is shown on the left, a symmetrized state, and then one can write that in terms of all possible permutations of this basis here, with a degeneracy factor which takes into account that two particles can be kind of in momentum state.
Did we lose Raju?
I think so. It seems to be his connection. Let's wait a moment if we can reconnect.
Well, I wrote him an email.
Hello, can you hear me?
Hello. Yes.
Yeah, my laptop died, so I apologize. So I can kind of restart. I'll stop my video though, just to be safe. Can you hear me?
Yes, very good.
Okay. So I realize I'm way over time, but I will try and I'll try and finish very quickly. So anyway, I was just saying that one can implement this this permutation by a series of Hardemud and swap and C-naught gates in some systematic way, which we have worked out. That's in progress. So this is my last but one slide. So now one can sort of set up the scattering problem. So you can prepare n external particles in terms of these, in terms of qubit registers. You can sort of write down a quantum circuit which does both symmetrization of this initial state, and then you can sort of do the time evolution of this object here, where we use trotterization. So you can sort of break this up into these little u's here, corresponding where little t corresponds to a trotter step. Right? So and then finally you want to do a measurement by turning off the interaction and measuring asymptotic single particle states. Okay, so this is kind of in this single particle approach, it's kind of natural to implement. So now the big thing, okay, now is how do we compute this, right? So take for example a scalar field theory, where you have a free part and an interaction part. So the free part is fairly straightforward to realize in this single particle basis. There's a circuit that we have written down in order to do that. I mean, it's non-trivial but straightforward. The really difficult part is this interaction term that one has, which is local in the coordinate basis. So the free part we compute straightforwardly in terms of phase rotation of single particle basis states in momentum space. But then to compute this, one can't do this in the p basis, and one has to go to the x basis. And so the way to do this is a kind of squeezing operation, where you can start with, so these particle states in momentum space, you can do a kind of squeezing operation to extract the, instead of these little a creation relation operators, you can extract the capital A. So this is a kind of squeezing operation, because the Fock eigenstates are not the single particle eigenstates. And then you can sort of do the quantum Fourier transform to construct the particle states in the position basis, compute this object interaction part here, and then go all the way back. Okay, so this is kind of the strategy that follows. So here's kind of the summary of where we are in this approach, in the worldline approach. So, and I've represented this in terms of two approaches here in comparison to that of Jordan-Lee and Preskill. So in our case, the basis states are these m particle qubits, right, corresponding to the m particles that are involved in the scattering process. And so the Hilbert space of each of these particles is fairly simple. It's just it's log of n to the d, where these correspond to the different momentum states that one can have. So it's a finite number of qubits that one has representing that, and m is the number of particles. In contrast, in the Jordan-Lee Preskill basis, that of local Heisenberg field operators, which are phi and pi, you are doing this it's a sort of lattice discretization. So the number of qubits is is n to the d, corresponding to each lattice site, and where d is the number of dimensions. And then for each of the momenta, you have log of k. That's the size of your Hilbert space here. So at least in this, it looks kind of promising in terms of that one needs a smaller basis. And then there's the issue of how one does a time evolution for this, as an example for the scalar theory. So now in the Jordan-Lee Preskill case, it's, since one is working in the space of field operators, then the evolution is just a straightforward trotterization. So you get into the d trotter terms for evolving this part of the phi terms. You can do a quantum Fourier transform and then evolve the pi terms and so on, and then repeat. Okay. In our case, it's quite a bit different, because you kind of have a essentially free evolution in single particle basis, which is order m trotter terms. So it's much fewer, where m is the number of particles. But then you have to do a quantum Fourier transform and squeezing to try and compute this interaction term in a single particle basis. We have to go from the p basis to the x basis, and then do a quantum Fourier transform back after performing this operation. So this part is what we are trying to work out in terms of what the complexity is, and if it's really on some power of m, or even possibly faster, then we are really in business in trying to implement this single particle digitization strategy to performing a first non-trivial computation of amplitudes. The measurement is relatively straightforward in our framework, because the scattering amplitude is diagonal number of particles, while in the Jordan-Lee Preskill case you need additional basis transformations. Yeah, I'm done.
Yeah. Can I have a question about this table?
Sure.
I'm a bit confused about the comparison. So I'm not familiar with the great details of the Jordan-Lee Presco paper, but it looks, I mean, as you were describing this, it looks like a discretization of a full field theory on some lattice, right? Whereas like the approach that you were describing is discretizing some part of the field theory and then leaving the gauge fields intact, right?
Right. So yeah. So thanks for that question, because that part I didn't really go into. So when I was discussing this, I started with kind of our kind of full problem, right? And I said, okay, I want to understand sort of digitization strategy for these bosonic whirl lines. Okay.
Yeah.
And of course, these are in some gauge field background. But then I decided to consider a scalar field theory to try and understand, how to digitize that problem. And if I can do that, then I can do it for these bosonic degrees of freedom. Okay, so I decided to just consider the explicit example of a scalar field theory in that case here. And then if we understand that, then we can kind of come back to this problem and treat this hybrid problem fairly straightforwardly.
Also, so your claim is that you came up with a simply better, faster algorithm for scalar field theory.
Yes.
Oh, okay. Thanks.
Yeah. So, but it was kind of motivated by this single particle, because the sort of previous approach was really to formulate, sort of really a discretization of the field theory directly, right? And then writing that in a spinor basis and putting it in a quantum computer and doing a real-time computation, right? And there's a certain scaling complexity in doing that. Here is in this hybrid approach is saying, well, okay, I'm just going to think in terms of a single particle kind of framework, right? Which may be appropriate for certain kinds of problems like scattering amplitudes, right? Where I measure a finite number of particles in the in and out state. And also the advantage being that, at least in the QCD case, I can kind of separate this out from the gauge field dynamics. So in principle, I can think about in QCD, if I want to compute, say, an n loop scattering in some background field, okay, of particles, right? So I can go to, say, very high loop order in computing scattering amplitudes, so in perturbative calculations, for example, these background fields are just plane waves. So in principle, one can do a perturbation theory problem to high accuracy, but that involves understanding this kind of digitization strategy for how one computes these X. And that's kind of what motivated us to take a step back and say, well, how would we formulate this in a scalar field theory? I hope that was...
Oh, sorry, I had the microphone muted. Yeah, thanks. Got it.
So just, so I apologize. I went way over time. I think I started a little bit late, but okay, still. So just to summarize, I mean, the whirl line formalism is a powerful method to compute scattering amplitudes, as I mentioned. And so it motivates thinking about a novel digitization scheme, which is alternate to what has been done in the literature for these bosonic whirl lines for implementation on a quantum computer. And as I said, the work that we've done in a scalar field theory is promising. We don't see any showstoppers yet. And we hope to have clear scaling estimates relative to Lee, Jordan, and Presco in terms of how you scale with the size of a Hilbert space and the number of particles and so on, the number of Trotter steps. So all of these things that we have to work out and really see there's a genuine advantage compared to Lee, Jordan, Presco. If that's the case, then we can now combine that in this hybrid approach with these classical gauge fields, and then take a first step towards a quasi-real quantum computation of scattering amplitudes in 3+1 dimensions. Now, I mentioned these Rishon representations of the Kogut-Susskind Hamiltonian in these quantum link models. These Grassmannian variables that we have for internal symmetries, they look very similar to this kind of Rishon representation that one has, and in principle, in the UV, we believe they may be the same thing. So one can then think of some kind of RG approach where one sort of has these kind of gluonic word lines, which are essentially these resonance, and which are the UV, which are then coupled to these quantum link framework in the IR, representing the gauge fields. And then there could be some kind of RG that kind of allows you to kind of go from the UV towards the IR. And the question is then, is there some non-trivial fixed point in that approach? So these are kinds of very vague questions that we are starting to also think about. So, okay, thank you very much, and I apologize for going over time.
Thank you very much for your talk. It's not so easy to give applause from overseas, but let me thank you for the very clear talk, and of course we have time for questions. Maybe let me directly start. So, wondering, so in terms of like doing computations on a quantum computer, this seems to be still limited to low dimensional systems. Could you study like full QCD in this framework that you presented, or would there be?
Yeah, so the idea is to study quote unquote full QCD in a hybrid framework. So this picture that we have is where we are representing the we are really starting with QCD in 3+1 dimensions, but then the gauge sector is treated somewhat simply, while the kind of fermionic sector, if you like, can be represented more non-trivially. But again, some aspects of the gauge sector, sort of the UV parts of it, can be also absorbed in this kind of digitization strategy as well. So for example, the example I gave is that suppose you want to compute, say, an N-loop QCD amplitude, right? Perturbative amplitude. So you want to compute, N, quarks and gluons coming in, and they have, multi-loops, and then they go out to M particles. In perturbation theory, one can represent the background gauge fields, relatively simply, and it's a sort of plane wave representation. And then the question is really computing that scattering amplitude on a quantum computer. Okay, so this kind of strategy would allow you to do that in principle. So with certain kinds of problems, it can be very, very efficient. Now, in QCD, even if I want to compute, say, an M-to-N scattering amplitude, in perturbation theory, that it's getting very complex very quickly, right? So this would be done, exponentially faster, potentially, using this approach than just perturbation theory. So that's the particular advantage in this context. Now, of course, to make real progress along the direction of what you're asking, one would then have to think about how you treat really the gauge fields in full generality on a quantum computer. And that's a very hard problem where there's a lot of serious work going
on. I see. And I guess in particular in one dimension, I guess 12 QCD, at least part
right.
of some maybe static properties analytically. So can you would your approach still approximate the gauge field classically for this?
Right. So people have, of course, looked at things like the Schwinger model and so on, and tried to really solve that in full generality on a quantum computer, in 1+1 dimensions. And even that's quite hard, and they can't really do more than sort of a few qubits, so on, and there are serious error issues and so on. So there are really two tacks one can take. I'm just pointing to a different class of sort of hybrid problems that one can address. So I should mention that in quantum chemistry and in condensed matter physics, there are also such hybrid approaches to deal with a variety of problems. So, for example, if you have correlated electrons in some very non-trivial background, this so-called dynamical mean field theory, you can treat part of the problem again on a quantum computer, and the rest can be treated in some kind of, you know, classical approximation to the problem.
So following on Johannes's question, I mean, in 1+1 dimension, the scattering trivializes, I guess. But on the other hand, you can attempt to represent interesting states in a classical computer using tensor networks.
Right. Yeah.
So do you see some interesting lessons that you can draw from such place?
Yeah, potentially. So one could think of this hybrid as where one uses tensor networks to construct such background fields, right? That's what you had in mind.
Yes.
Yeah. So
I'm not even sure if you would have to, you know, really take out fermions from the picture the way you do this, and like maybe it's not even needed.
Right.
But the question is like, is there some interesting lesson that one can draw or extract? Because I mean, possibly something can be done, and it's not very well explored, like time dependence in this context. In particular, time dependence in quantum field theory using tensor networks is not something that is well explored.
Right.
But if there is something interesting to learn, I think like that's probably within reach.
Right. So I think for scattering problems, you know, especially, I mean, issues, you know, state preparation, right? So this, for example, the high energy limit of QCD, which is kind of the ultimate, you know, interest that I have, right? So there, the state is very complex, right? I mean, you have this very dynamical, complicated state. So, you know, preparing that state is highly non-trivial, right? So I'm sort of, the strategy is really I'm trying to develop as a way to kind of get there. And so even if I were to do the scalar field simulation 1+1 dimension, I mean, it's still pretty non-trivial, you know, in terms of, you know, in terms of actually implementing this.
I have not said that it's not. I'm just saying that it's it might be to some degree feasible, nothing more. I mean, if the state is highly entangled, then of course these methods face their own limitations, right? So there's always some threshold what can be done. But anyway, thanks.
Yeah.
I wanted to get your feeling on this.
Yeah.
Okay, are there further questions? If not, then let's thank again Raju.
Yeah, thank you very much.
Thanks, Raju.
Thanks.